the pill.
Receptor pharmacology, theories of drug receptor interactions. Occupation theory. Hey everyone, welcome back to our channel. Today, we're diving into the fascinating world of drug receptor interactions, specifically focusing on the occupation theory. So, grab a seat, buckle up, and let's get started. First things first, let's break down what the occupation theory is all about. This theory, proposed by Alfred J. Clark in 1937, suggests that the response to a drug is directly related to the occupation of receptors by an agonist. Now, let's talk about the assumptions made by Clark. He proposed that there's a linear relationship between receptor occupancy and response, with the maximal response occurring when all the receptors are occupied. To understand this better, let's introduce the concept of equilibrium dissociation constant, KD. This value helps us determine the affinity of a drug for the receptor. It's calculated using the rates of association and dissociation of the drug-receptor complex. Now, let's look at how the concentration of a drug relates to the response. According to the occupation theory, the relationship can be expressed using a simple equation, which gives us a hyperbolic curve when plotted. Moving on, we have intrinsic activity, denoted by alpha, which determines the strength of the pharmacological stimulus produced by receptor occupation. This is where we also introduce the concept of partial agonists, which have both agonist and antagonist properties. Next up, we have efficacy, represented by the symbol E, which is the capacity of a drug to initiate a response once it occupies receptor sites. We'll also touch on the idea of spare receptors, which have important implications for receptor blockade. Let's not forget the rate theory, which focuses on the rate of association and dissociation of the drug-receptor complex. This theory also helps us understand the characteristics of antagonists. Lastly, we'll explore the operational model theory, which provides a unified view of receptor occupancy, stimulation, and the production of response through cellular processing. It's a bit more complex, but we'll break it down for you. Rate theory. So, what exactly is rate theory? Well, it's a theory that focuses on the rates of association and dissociation between a drug and its receptor. In simple terms, it helps us understand how quickly a drug binds to and unbinds from its target receptor. One important concept in rate theory is the equilibrium dissociation constant, KD. This is the concentration of a drug that produces half the maximal equilibrium response. In other words, it's a measure of how tightly a drug binds to its receptor. According to rate theory, antagonists have a low rate constant of association, K1, and a very low rate constant of dissociation, K2. This means that they bind to the receptor slowly and stay bound for a long time, effectively blocking the receptor from other drugs. Now, one of the key observations that led to the development of rate theory is the hyperbolic relationship between agonist concentration and tissue response. This means that as we increase the concentration of an agonist, the tissue response reaches a maximum and then levels off. To understand this relationship, scientists like J.W. Black and P. Leff developed the operational model. This model provides a unified view of receptor occupancy, stimulation, and production of response through cellular processing. It assumes no cooperativity between receptors and that the relationship between stimulus and overall response is controlled by a hyperbolic function with a slope of 1. In the operational model, the response can be expressed as response equals A tau Emax / A tau plus 1 plus Ka, where tau quantifies the power of the agonist to produce a response, efficacy, and the ability of the system to process receptor stimulus into a response. Operational model theory. Let's start by understanding what the operational model theory is all about. This theory provides a unified view of receptor occupancy, stimulation, and the production of response through cellular processing. In the operational model, the response is expressed in terms of receptor and tissue parameters. It allows us to quantify the power of the agonist to produce a response, known as efficacy, and the ability of the system to process receptor stimulus into a response. Now, let's break down the mathematical representation. The response, E, can be expressed as a function of the agonist concentration, A, efficacy, tau, and the ability of the system to process receptor stimulus into response, Emax. The equation for the response in the operational model is response equals A tau Emax / A tau plus 1 plus Ka. Here, tau quantifies the power of the agonist to produce a response, and Ka represents the equilibrium dissociation constant. Understanding the operational model theory has practical implications. It helps us comprehend how different drugs may have varying capacities to initiate a response and occupy different proportions of the receptors when producing equal responses. To visualize this, imagine theoretical log concentration response curves for agonists having different values of efficacy but the same affinity. This can help us understand how the efficacy of a drug impacts the response it produces. In the real world, this theory is crucial for pharmacologists and drug developers. It provides insights into how drugs interact with receptors, and how the efficacy of a drug influences its ability to produce a response. Induced fit theory. A receptor undergoes conformational changes when a drug is at the receptor site, termed biophase, to allow effective binding of the drug to the receptor. Induced fit of drugs to receptors may lead to additional binding to secondary active sites, which may prolong the duration of action of drugs on the receptor. Macromolecular perturbation theory combines the rate theory and induced fit theories. Postulates that two types of conformational changes occur. The rate of the existence of the two conformational changes determines the observed pharmacological response. Agonists produce their required conformational change for the observed pharmacological response. Antagonists produce a non-specific conformational change that fails to produce a pharmacological response. Theory may partially explain the activity of partial agonists, which produces a partial pharmacological response regardless of drug concentration. Activation aggregation theory. Receptors are always in a dynamic equilibrium between inactive and active states. Agonists shift the equilibrium in favor of an active state, leading to a response. Antagonists prevent the activated state, thereby blocking the response. This theory explains the activity of inverse agonists, which elicit an opposite response compared to traditional agonists. Now, let's break down some of the key terminologies. Receptors. These are the specific sites on cells or tissues where drugs bind to produce a response. Agonists. These are drugs that bind to receptors and activate them, leading to a response. Antagonists. These are drugs that bind to receptors but do not activate them, thereby blocking the response. Inverse agonists. These are drugs that bind to receptors and elicit an opposite response compared to traditional agonists. The activation aggregation theory provides a comprehensive understanding of how drugs interact with receptors to produce specific responses. This theory is crucial for understanding the effects of various drugs and their mechanisms of action. Well, that wraps up our overview of receptor pharmacology and theories of drug-receptor interactions. We hope you found this video informative and interesting. Don't forget to like and subscribe to our channel for more interesting content like this.
PharmaPal.